All right, let me talk about randomization tests. So the example I'm going to do is going to be comparing proportions. So here's just kind of a simple example. Is the proportion of international students different for stats and data science majors and data theory majors? So I'm completely just making up these numbers, so don't quote me. But let's say we get a random sample of 150 students majoring in stats and data science, and we find that 75 of them are international students. And then we get a random sample of 160 students majoring in data theory, and 64 of them are international students. So the question is, does this provide evidence that the proportion of international students is different for students majoring in statistics and students majoring in data theory? So the way we would run a test like this would, the traditional way would be to do a z proportion test. So we would calculate proportions. Another way would be a chi-squared test, but mathematically they're actually equivalent. But anyway, so we would say, okay, for the stats and data science majors, we had 75 international students out of 150 students total, and so therefore our proportion is going to be 75 divided by 150, or 0.5. For data theory, we had 64 international students out of 160 students total, so 64 divided by 160 gives me 0.4. And so if you take the difference between 0.5 and 0.4, you get a difference of 0.1, or 10 percentage points. The null hypothesis would be that the two groups have the same proportion of international students, and therefore there's zero difference between the proportion of international students for the two majors. So our null hypothesis would be that if we did p stats minus p data theory for the population, we would get a difference of 0. The alternative hypothesis would be that the difference between the proportion of international students in stats and international students in data theory is not 0. Okay? And if the null hypothesis were true, then we would expect, whenever we take random samples, we expect the difference between proportions to be around 0. We happen to get a difference of 10 percentage points. So is that difference statistically significant? Okay, well, according to the central limit theorem, we can approximate the sampling distribution of that difference with a normal distribution. If the null hypothesis were true, we expect the mean to be centered at 0, and then the standard error for this sampling distribution would have this equation, okay, where p hat is kind of your overall proportion, and you take kind of the overall proportion 1 minus that times this, okay, and we would expect, this value to be centered at 0 if that null hypothesis were true. And in our case, we would calculate the p-value, which is the probability of getting our difference, or something more unusual, something more extreme, if the null hypothesis were true. In our case, we observed a difference of 10 percentage points. So the observed difference, or something more extreme, would mean we're looking for what's the probability that the difference is, the absolute value in difference is greater than 10 percentage points. Okay, what's the probability that the absolute value is greater than 0.1, and we're doing the absolute value because it's a two-sided test. It would be interesting to us if the population showed that the proportion of stats majors, or proportion of international students in stats, is greater than the proportion of international students in data theory. It would also be interesting to us if the proportion in data theory was greater than that in the proportion in stats. Okay, so either of those differences would be interesting. So, we would go for kind of both a positive or a negative. And so here, to kind of get both the positive or negative sides, we do the absolute value. Is the absolute value greater than 10%? So this is how you would go about doing the math. So we had 75 out of 150 for stats, 64 out of 160 for data theory. So a total of 75 plus 64, so what's that, 139, divided by a total of 310 students. And so our overall proportion is 0.4484. Okay, we would plug that in to our standard error, and so our z-score is going to be our observed difference of 10 percentage points divided by the standard error. So when you compute all of these numbers for the standard error, you plug in all of the values that you have, you get a standard error of around 0.0565. So this gives us a z-score of, around 1.77. So we want to know, okay, what proportion, what is the corresponding z for, what's p norm of, say, 1.77, okay? And we get 0.03836, okay? And basically we want, double that. So my p-value ends up around 8%, 0.076, okay? This would be my corresponding p-value. This is a probability of getting a difference of 10 percentage points or something more extreme, okay? So here's our probability. This is kind of our diagram. And so here we observed a difference in 10 percentage points. What's the probability of getting out here? It's symmetric. We have around 0.0384 out here, 0.0384 out here, for a total of around 7 percentage points. Okay, 7 to 8%. Okay, so our p-value is, say, 0.0768. Let's say our significance level is 5%. In that case, our p-value is greater than alpha, and we would not reject the null hypothesis. Okay, here the data we have does not provide enough evidence that the proportion of international students for stats majors is different for stats majors and data theory majors. Okay, so if it were the same, okay, so let's say the two populations have the same proportion of international students. When you draw random samples, we would expect our random samples to have samples where the proportion is the same. Okay, we expect samples drawn from each population to have the same proportion of international students. Okay, but because of the random sampling process, you can still produce two random samples where you end up getting a difference of 10 percentage points, 0.1. How often does something like that happen by random chance? It happens with a random chance with a probability of around 0.0768. So not a huge probability, but also not small enough that you can just completely dismiss it. So we can't say that this difference in 10 percentage points was caused by anything other than random chance. Okay, so that's kind of how you would approach that. Now, the conditions to the z-test, the z-test relies on the central limit theorem. So to use the z-proportion test, your samples have to be large enough. And general consensus is that you need at least 10 yeses and 10 nos in both samples. Now, in our previous example, we had more than that, right? So in our numbers, we had 75 yes, which would mean we had 75 no, 64 yes, and 96 no. Okay, and we had at least 10 yeses and 10 nos in each sample. Okay, so we could use the z-test. But if you don't have a big sample, then using the z-test could lead to the wrong value and could lead to the wrong conclusion. So in the cases like that, you'd want to use a randomization test. So there's a video on Mythbusters, and unfortunately, I cannot play it for you because it's copyright protected. You can click this, but it'll take you to a page on YouTube where you have to purchase the video. So, unfortunately, I can't record it and post it to YouTube. Otherwise, I get a copyright strike. So I'm gonna just have to kind of describe to you what happens in the video. It's from an old TV show called Mythbusters. Okay, and in that TV show, they had this question of, is yawning contagious? Is yawning contagious? And so what they did was they ran an experiment, and they found they went to like a flea market, and they asked for volunteers, and they found 50 volunteers who are willing to participate. And basically what they did was they had each participant sit alone in a small room, and they were video recorded. And while they were sitting in the room, they just waited to see if that participant would yawn or not during the time that they were sitting in the room. Okay. Now, however, before they entered the room, okay, some of the participants saw the kind of saw the host, or basically the person running the experiment. That person would intentionally yawn like right in front of that participant, and then that participant would go into the room, and they would see, that would be basically the treatment group or the CDON group, and then other people did not see anybody yawn, okay, and they sat down in the room. So basically, that formed the treatment group and the control group. And so, some people saw someone yawn right before they entered, other people did not. Okay. And then based on that, and the outcome variable was while they sat in that room, did that person yawn or not? And they wanted to know, is there a difference in the proportion of people who yawn based on whether they saw the seed yawn or not? Okay. So that was kind of the experiment. I hope I explained that okay. So some people saw somebody yawn before they entered the room. Other people did not. And then the outcome is, while the person was sitting in the room, did they end up yawning themselves or not? Okay. And now technically, the way they set it up, the sample of people were not randomly selected. Okay. However, the treatments of who saw somebody yawn or did not yawn, that we can treat that as being randomly assigned, because what they said was every third person was a control, and then the other two were put in the treatment group. So the order of participants who kind of lined up is random, so we can kind of treat this as randomly assigned. All right, and then here's the data that they collected. Okay, there were for 34 people got the CDON. Before they entered, 34 people got the CDON, and then out of those 34, 10 of the people ended up yawning while they sat in the room. So the proportion of people who yawned in the CDON group, 10 divided by 34, 29%. Okay. The remaining 16 participants, remember there were a total of 50 people, okay, did not see anybody yawn, okay, and out of those 16, 4 people yawned while they were sitting in the group, okay, and so the observed proportion there of people who yawned was 4 out of 16, around 25%, okay, and so the people in the show, they were saying, well, the difference isn't huge, but because, it's based on such a large sample of 50 people, they came to the conclusion that, this difference of 4 percentage points is enough to make the conclusion that yawning is contagious, that seeing somebody seed yawn made them more likely to yawn than if they didn't. Okay, that if you didn't see anybody yawn, you're only going to yawn with a probability of 25%. After seeing someone yawn, your probability went up to 29%. That was their conclusion. And the narrator says, there's little doubt it does seem to be contagious, that yawning is contagious. So I want to take this data and perform a hypothesis test, okay? And so the notation we're going to do is we've got probability seed and probability control. So probability seed is for those in the seed group, what is the probability that they would yawn? Okay, so the probability of yawning if they're in the seed group. P control is going to be what's the probability that they yawn if they're in the control group. Our null hypothesis is that yawning is not contagious, that whether you're in the seed group or whether you're in the control group, the probability that you yawn is the same. So probability of yawning in the seed group minus probability of yawning in the control group, that difference is going to be 0. Okay? The alternative hypothesis is that yawning is contagious, that if you get the seed yawn, you're more likely to yawn than the person in the control group. So probability of seed minus probability of control is going to be greater than 0. So this is not going to be a not equal sign. We're only interested in one side, and that is only if the seed yawn group has a higher probability of yawning than the control group. So our data has a difference of basically 4 percentage points, 0.044, 4.4 percentage points. And that's found by doing 10 over 34, or 29.4%, minus 25%, 0.044. So if the null hypothesis were true, would we expect the observed difference between proportion? If this null hypothesis were true, we would expect the difference in proportions to be around 0. We're getting a difference of 4.4 percentage points. And so the question is this difference statistically significant, or could it just be due to random chance? So our samples are not big enough for us to do a z proportion test, because I need at least 10 yeses and 10 nos. And here I have 10 yeses and 24 nos for the seed group, but I only have 4 yeses and I have 12 nos in the control group. So I don't have enough to do a proportion test. Okay. Let me just talk a little bit more about the null hypothesis. Here, the null hypothesis is that yawning is not contagious, that the probability of yawning is the same for seed and control groups. If the null hypothesis were true, then whether a person yawns or doesn't is independent of whether they got the seed yawn or not, meaning that the observed difference, is just a result of kind of randomness in the assignment of treatments. Okay. Another way to think about that is, out of the 50 people, 10 plus 14 are just kind of like destined to yawn. It had nothing to do with whether they saw the person yawn or not. These 14 people, they were just going to yawn no matter what. Okay. And if the null hypothesis were true, then we're basically saying that the fact that one group got 29% and the other group got 25% is just a result of random assignment. And that random assignment could produce the difference in proportions of 4.4%. That's what, if we assume the null hypothesis were true, that's basically what we're saying, is that, these results that we got back here, this could have been just due to random assignment, not anything to actually do with the control group or the seed group. And so to kind of put that to the test, we can do a randomization test, okay? The p-value that we observed, okay, or the p-value that we're going to calculate, okay, is the probability of getting our difference or something more unusual, more extreme, if the null hypothesis were true. Again, if the null hypothesis were true, we would expect the proportion of yawners to be the same for both groups. We would expect to see a difference of 0. We got a difference of 4.044, 4.4%. So, if the p-value is, if we assume that the two populations have the same proportion of yawners, then what is the probability that random assignment could produce samples of data where the difference is 0.044 or something larger? Okay. Again, we can't use the z-test because our samples are too small. So with the randomization test, we're going to simulate the sampling distribution of outcomes when the null hypothesis is true. We're going to just say, well, let's just assume the null hypothesis were true, and let's see what kind of results we could get when we do the randomizing ourselves. Okay? And so what we're going to do is we're going to say, well, what is the null hypothesis? The null hypothesis said there's 50 people and 14 of them are destined to yawn. Okay, that's what the null hypothesis. And then we're going to just say, if the null hypothesis were true, then who ended up in one group and who ended up in the other group is just a result of random assignment. So I'm going to have like 50 people. We're going to say 14 of them are destined to yawn, but I'm going to mix everybody up, and I'm going to put 34 into group A and 16 into group B. This is just going to be completely random. All right? And then we're going to say, okay, out of those who ended up in group A, what proportion are these, yawners, okay? People who are destined to yawn. And out of group B, what proportion of people ended up being yawners, okay? And we know that who ends up where is just a result of the random process. It had nothing to do with anything else because we didn't do anything. All we did was we just shuffled them up. So we can, because we did the random assignment ourselves, we know that any difference we see between this group and this group is because of just the random assignment process, nothing else. And so we can see what kind of differences we end up getting through the randomization process. Okay? And what we'll do is we're going to repeat this randomization a whole bunch of times. Every time I repeat it, I'm going to record the difference between the group proportions. And after a whole bunch of iterations, we're going to have all of the different proportion differences that we can get, where our only source of randomization, only source of difference is the randomization process. Okay, and so the sampling distribution is going to show us what kind of proportion differences can happen even when the null hypothesis were true. Right, and what we want to know is our observation of 0.044, is that unusual or not, right? So that's what we got in our observed data. Our observed difference is 0.044. And when we look at the sampling distribution, we want to know if 0.044 is unusual or not. If 0.044 is unlikely to occur in the sampling distribution, then the fact that we got 0.044 in our data suggests that our null hypothesis is actually wrong. Okay, if it turns out getting 0.044 is really unlikely to occur, then from randomness, then the fact that we got that would indicate that it, something else other than randomness had to be the case. Okay. However, on the other hand, if it turns out we get a difference of 0.044 very frequently, if that's a common occurrence in our sampling distribution, then we're going to say, well, maybe the reason why we got 0.044 is just randomness, okay? Because, we generate this distribution from randomness, so maybe randomness can just produce 0.044 quite a lot. So, that's what we'll do, okay? Now, an important idea is there's exchangeability in our outcomes. So the key assumption for randomization or randomization test is that there's exchangeability. Exchangeability is that if the null hypothesis were true, all possible permutations of the data are equally likely, okay? And it means any one permutation of the data is exchangeable with any other permutation. On a practical level, this means that exchangeability applies only to experiments where random assignment was used, okay? If there was no random assignment in the gathering of the data, don't use a randomization test, okay? And the reason why you can apply exchangeability to random assignment is just that if the patients are treated or are assigned treatments randomly, then you could just imagine if somebody ran the experiment on another day and just kind of clicked the randomize button, and you end up with a different, person number one ended up in the treatment group in one thing, and then on another day, if they did the random assignments again, person number one could end up in the control group, right? We're just saying any arrangement of who ends up in the treatment group and who ends up in the control group is just as likely as any other arrangement, okay? At least at the start of the experiment, all right? If that null hypothesis is true. So in cases where treatments are not assigned randomly, that is an observational study, the permutations of the groups are not going to be equally likely. We can't use the randomization test, okay? All right, so this is how I'm going to simulate the randomization test or run the randomization test on the computer. First, I have to create a vector representing my data, okay? This is going to be all 50 people, okay? All 50 people. And I'm going to say true means they yawned, false means they didn't yawn. And so in the treatment group, I had 34 people, 10 of them yawned, 24 did not. So I'm repeating true 10 times, false 24 times. In the control group, I had 16 people, 4 of them yawned, 12 did not. So I'm going to repeat true 4 times and false 12 times. And I'm going to just say, so this is a vector. Yawning is a vector of length 50. where I have a total of 14 trues and 36 falses. 14 people who yawned, 36 people who didn't. And right now, it's set up so that the first 34 values represent my treatment group, where 10 yawned and 24 did not. And then the last 16 values, that is values 35 through 50, 4 people yawned and 16 did not, and that represents my control group. So I could say, hey, what is the mean of the treatment group? 10 out of 34, 29.4%. What is the mean of the control group? Okay, there's 16, 4 out of 16, 25%. And I could say, okay, what is the observed difference between proportions? I do, 0.294 minus 0.25, I get 0.044. Okay, that's my observed difference. So yawning represents the 50 individuals. Again, 14 of them are true, representing that they yawned. 36 are false, representing that they did not yawn. And so what I'm going to do is I'm going to take all 50 values and I'm going to shuffle them, okay? And so that's going to be sample, right? When you call sample on a vector, it basically shuffles the contents of the vector. All 50 values remain in that vector, but the order is now randomized, okay? So after I call sample on that vector yawning, I'm still going to have 50 values. 14 are true and 36 are false, but the order is randomized, okay? And so one example is I run sample, so now it's all mixed up, and then I'm going to just take the first 34 and put those into group A. So I just know the 34 true-false values that end up in group A are just a result of randomness. And then I'm going to take the remaining 16 and put them into group B, okay? And I know the 16 values that end up in group B, that's just a random process, has nothing to do with anything else. It's just, I ask the computer to just randomize them, sample, so these are all just shuffled and randomized. Who ends up in group A and who ends up in group B is just purely a result of randomness. And I say, okay, well, how many true values do I have in group A? It turns out 10 out of 34, 29.4%. How many true values do I have in group B? Okay, 4 out of 16, 25%. So just by coincidence, okay, when I randomize this, I ended up getting 0.044, same as my observed sample. But this is just one random example, okay? So, we randomly assigned 34 people to group A and the other 16 to group B. 29% of group A were yawners, 25% in group B were yawners. Our random process happened to produce a difference of 0.044 just by randomness. This seems to be just a coincidence, but we'll run a bunch more trials to see, what could happen. And again, we know this is just the result of just the random process. Okay, so here I just pick another seed and I shuffle up my 50 true-false values again, and then I say, all right, let's put the first 34 into group A, the remaining 16 into group B. So I go 1 through 34 is group A, 35 through 50 is group B. And so again, who ends up in group A, or which true-false values end up in group A and which true-false values end up in group B, is just purely a result of the randomness introduced by sample, okay? Nothing else. And so in this case, I got 0.235, 23.5% of group A yawned, 37.5% of group B yawned, and so I'm getting a difference of negative 0.1397, negative like 14%, okay? So that's a possibility, okay? So here I'm going to do this a whole bunch of times. I'm going to say, let's do this 10,000 times, and we're going to keep track of all of the differences that we see each time, okay? So look, my loop is very simple. I just say for I and sequence along differences, basically for I in 1 through 10,000, okay? Take that yawning vector of 50 values and just shuffle it. Call sample on yawning, okay? That's going to give me a randomized vector. I'm going to say, all right, take the first 34 and throw them into group A. Take the remaining 16 and throw it into group B, okay? And the reason why I'm doing 34 and 16 is because in the original data, that's what we had. Okay, in the original data, there were 34 people in the seed group and 16 people in the control group. So I'm just trying to simulate the idea of creating two groups of the same size. But here we're saying, you know, I'm not doing actually like yawning in front of them, and I'm keeping other people away from the seed yawn or doing a control thing. We're just seeing like what could happen if we just shuffled the people up. Let's just assume 14 of these people are going to yawn anyway, and let's just shuffle them up. Let's see what kind of things could happen. And we know that there's no like, we're not doing any actual experiment here. We're just shuffling people up and just seeing like what happens when we shuffle things up, right? Assuming just 14 people are going to yawn anyway. And so we put 34 people in group A, 16 people in group B. I say, all right, what's the proportion in group A? What's the proportion in group B? And what's the difference? And we take that difference and we record it. Okay. And what do we see? We see sometimes we got a difference as big as negative 0.599, like a negative 60%. Sometimes we got a difference as high as positive 0.411. Okay. Our median difference, 0.044. Okay. Which is exactly what our observed difference was. Okay, so my observed difference was 0.04411,765, which happens to be our median value. And we could say, well, all right, well, what is the probability that the randomization process produces a difference that we observed or something greater? All right. So we're really only interested in getting a difference of 0.044 or something more positive. So here I'm going to say, all right, of the differences, how many are greater than or equal to observed differences? This is going to, this part right here produces a logical vector. If that difference is greater than 0.044, then you get true. And if it's greater than or equal to observed difference, then you get true. And if it's not, then you get false. And then we're going to take the mean of them. So we're going to get the proportion of differences that are greater than or equal to the observed difference. And it says 50%, okay, over 50%. Over half of the 10,000, when I randomize this 10,000 times, we got a difference of 0.044 or something greater than that over 50% of the time. So this is not an unusual outcome by any means, okay? So, you know, the Mythbusters video was like, oh, this difference of 4%, you know, it's not huge, but it's significant. We definitely say yawning's contagious. It turns out, no, you could have gotten this difference just kind of by random chance, okay? You could have gotten this difference just kind of by random chance. So you know, we're not convinced that this produces evidence that yawning is contagious, okay? So our empirical p-value is 0.507. We're saying the randomization process has a high probability of producing the data that we observed in the Mythbusters experiment. So we have no reason to believe that the data we observed was caused by something other than randomness, okay? And we would not reject the null hypothesis. And we'd say the data does not provide reason to believe that getting a seed yawn makes a person more likely to yawn, okay? On the other hand, we cannot conclusively say that yawning is not contagious, okay? Our data simply doesn't provide evidence that it is contagious. So it is possible that a seed yawn actually does increase the probability of a yawn, but maybe we just didn't collect enough data, or maybe we happen to get some weird data that just leads us to believe it's not. Who knows, okay? Maybe yawning is contagious, but just, you know, the people who who were in the treatment group, just, you know, they were resistant to yawning. I don't know, okay? So we can't conclusively say yawning isn't contagious, but this data is not the thing that's going to prove it to us, okay? What would happen if you ask the question, does yawning have any effect, positive or negative, right? Maybe you see someone yawn and you're like, oh, no, I can't yawn. So we would be interested if there's a positive or negative difference, okay? So in this case, we would run the absolute value. We want to say like, okay, what, you know, positive or negative difference, okay? So if I say, hey, what proportion, if you check the absolute value of differences, what proportion is greater than our observed difference? you end up getting a p-value of 1, okay? And that seems kind of crazy. Anytime you get a p-value of 1, you feel like, oh, maybe I did something wrong, okay? But actually, that's exactly what we end up getting when you end up getting a p-value of 1, okay? And let me explain what's going on. So remember, there's 50 people and 14 yawned, okay? So there's a few splits, okay? So our current split, we said we did 10 out of 34 in group A and 4 out of 16 in group B, okay? And so this produces, if you do 10 out of 34 minus 4 out of 16, you get a difference of 0.044, okay? Is the difference. Okay, so there's only a finite number of ways to split, okay? You could end up with, say, 9 out of 34 in group A. And that means, you know, a total of 14 people. So that means it has to be 5 out of 16 in group B, okay? So here, if you do 9 out of 34 minus 5 out of 16, okay, your difference is negative 0.0477 difference, okay? If you do anything else, say like 8 out of 34 and 6 out of 16 for A and B, then what kind of difference do you get there? 8 out of 34 minus 6 out of 16, you get negative, you know, your difference there is that. Okay, what if you go the other way? 11 out of 34 for A and 3 out of 16 for B, okay? 11 out of 34 minus 3 out of 16, you get a difference of positive 0.0136 difference, okay? And so you can see that because there's only a finite number of people, there's only 14 people who yawned, there's only a few ways you can really split those people into two groups, group A and group B. You can either put 10 and 4, 9 and 5, 8 and 6, 11 and 3, and any difference other than 10 and 4, when you check the absolute value, they're all greater, okay? The absolute value of this is greater than 0.044. The absolute value of this, is greater than 0.044. It is, so if the null hypothesis were true, we said we would expect a difference of 0, but it is physically impossible to get a difference of 0 in the proportions because the way the data is split, where you have 34 in one group and 16 in the other group, it is not possible to get a difference of 0 because you have 14 people who yawned total. The closest you can get in proportions is 10 out of 34 versus 4 out of 16 for a difference of 0.044, okay? You do any other kind of arrangement of individuals, you're going to get a difference of proportions that's slightly bigger than 0.044, okay? Or maybe a lot bigger than 0.044. It is literally impossible to get a difference between proportions that is less than 0.044. So when Mythbusters is looking at their example and they say, you know, the difference isn't big, okay? The difference isn't big, but you know, we're convinced that that yawning is contagious, okay? It is actually literally impossible to get a difference that is any smaller than 4.4%, okay? So this is the smallest possible difference you can get. And so if you check, you know, for either positive or negative differences, yeah, you get a p-value of 100%, okay? Which seems kind of wild, but that's exactly what's going on in the data. It is not possible to get a difference between 0.044. Okay, but anyway, to sum it up, the key idea for a randomization test is you take your data, and then you shuffle all of those individual values, and then you randomly assign some to group A and the rest to group B, okay, according to how the observed data is arranged, and then you use that to kind of calculate the differences there. All right, and so this will give you your sampling distribution of differences, and you want to know of these differences, you know, how many differences are greater than whatever you observed. Okay. All right, so that is that for randomization tests.